I think you all know what is tensegrity. Actually, it is a structural principle by Buckminster Fuller. There are several definitions of this structure, but it depends on the field of the industry or the field of application that you want to consider. But the more common is by Buckminster Fuller, and Francois as is joining the meeting. He's joining the meeting. Okay. Welcome, Francois. Yeah, we are going to use this kind of structure as the first one. You see that basically it's a spatial 3D structure made up of solid or rigid bodies like bars, and also cables, which are basically pre-stressed elastic cables. Okay, you can think about them as pre-stressed elastic cables. This is what we are going to simulate in Kangaroo, actually. And the tension provided by this cable is capable of maintaining the rigid bodies like these beams or these bars in a three-dimensional configuration. Okay, and the idea is that, well, the phenomenon is that the more load you apply to this structure, the more stable it becomes. This is something that we will be able to analyze in the second example that we are going to simulate. Okay. So first of all, the real problem with tensegrity structure is not building or simulating a tensegrity structure, but understanding how to create the connections between the bars with these elastic wires. Okay, so you have to imagine how to anchor basically each end of each bar in 3 dimensions in order in order for this bar to be impossible to move in space while applying some loads. Okay, normally we will be working with some standard load, which is gravity, actually, in order to simulate these structures. But you can also apply other types of loads. You know that, for example, tensegrity is actually used also for designing some furniture like chairs and so on. Okay, so in that case, for example, you have to consider a load like a person sitting on the chair. But anyway, this is just values. Okay, so we are going to concentrate on this first structure here. That's why I placed the photo. And basically, in terms of Kangaroo, it's very simple to simulate this kind of structure in general, because you only need two sets of lines. Okay, you see that the black lines are actually sorry, the white line are actually the bars, and the black line are the cables, okay, or tendons, or how do you want to call them, okay? Once you detect or differentiate these kind of lines, then you simply apply different forces or different goals in Kangaroo 2 in order for them to have the right behavior during the simulation. So here you will see that the huge part is always defining the geometry of the system. Then you have some kind of very simple simulation based on elastic forces like springs, standard springs. And then there is a simulation, and then you might want to perform some kind of, let's say, further, let's say, definition that eventually gives some thickness to these elements or changes the colors, like I've done here. But it's just semantic. Okay, it's not that important. The important thing is the correct definition of the geometric system. Okay, and this happens before Kangaroo simulation. So I'm going to turn off the preview of the output here, and I'm going to concentrate on the definition of the system. Okay, so you see here I have this set of 3 by 3 points. Now, eventually, this is something that you might want to further investigate, but I would recommend that you start in this case with a polygon having 3 sides, like this. You can also select a point in order to place this structure wherever you want, actually, and give a radius with some 11 slider in order to have a wider polygon. Okay, so you can change everything. And then I'm just, as you know, I like to repeat the definition so that instead of having some simple description of what happens here, which is something that you might understand easily, I want to give you some optimized workflow in order to get to the same result. So I'm going to move this triangle up, like with Z vector and with another 11 slider, which is going to be quite higher in this case, like this. And so we have our two polygons. And also because if this is parametric, you can also increase the number of sides, for example, for the polygon, and have some kind of more complex structure. Of course, you will see it in a while. What we are going to do will be valid for the triangular polygon. Okay, so in case you increase the number of sides of segments, for example, you will have to reinvent the connections for the elastic wires or the cables or tendons. Okay, so we have these two polygons here, and I'm going to create a discontinuity component. I think we already discussed this, but if you have polygons, for example, or polylines, and you want to extract vertices, I do recommend that you work with discontinuity instead of explode, especially in this case, because if you have a closed polyline like a polygon, the number of vertices includes the double vertex that you have here at the start and end point of the closed polyline. So we just need the 3 points, and these are taken into account correctly by the discontinuity, which gives us 3 points. Okay, so that's why I'm using discontinuity, and I'm passing also the upper polygon. Now we have, let me get rid of these two here. Okay, now we have these 6 points in 2 branches because we are basically calculating the discontinuities for each of the 2 polylines. And so we have these 3 points. And now we are basically here, okay, with a different structure. But we can also take this tree here and explode this tree. We only have 2 branches here, and pass the first one here and the second one here. Just let me double check that these were the inferior points. So let's say that we have these 2 here. And then this is something that, for example, it's totally useless in case we were working with the polygons, because here I am creating the 3 cables at the base of the structure, and here the 3 cables at the top of the structure. Okay, but in case we have the polygon, the initial polygon, we just need to explode the polygons in order to have access to the 3 sides, which are the 3 lines of the polyline. So eventually I would create an explode and apply it to both polygons like this. So we also have our 6 segments here in the explode component. Okay, and then we also need to connect the vertices or the endpoints of this structure in diagonal. Okay, so say we have these cables here. Remember that we need to construct this kind of structure here. So we are defining we are going to define the bars in this case. You see that basically if you think about triangles, just keep in mind that in this case we are taking a look at the deformed system. Okay, but you have to imagine that before releasing this system, this vertex here is aligned with the lower one. Okay, so as soon as you release the system, this system will have some twisting that will bring these bars here to fall down, but they will be, let's say, kept in place by the 3 cables that are basically anchoring these endpoints. Okay, so we are constructing the undeformed system. Okay, so that's why, for example, in this case here, in order to create the diagonal bars, what I did was, once you have the points here, which are 3 at the bottom and 3 at the top, you will have some correspondence between this vertex and this one, because the upper polygon is just a displacement of the lower one. So what I'm going to do, I'm going to use a point list in order to visually take a look at this. So you see that, for example, you see 0.0 of the lower polygon corresponds to 0.0 of the upper polygon, but we need our bars to connect this point with this point, and then 1 with 2 and 2 with 0. Okay, so what I'm going to do, I'm going to apply a shift list to one of our polygon, for example, the upper one, one of our sets of points. Okay, say the upper set. So in this case, for example, I created an explode tree, which I need actually. So I'm going to shift list the upper set. Okay, so this is the 3 point. You see that the points are still the same, but actually what happened is that the set has been shifted by one position. So if I apply, for example, this point list to this, you see that now this has become 0, okay, and 1 and 2. So when I connect with a line, the first set of point with this second set of point, I will have diagonal connection. Okay, this is simple data manipulation in Grasshopper. So shift list allows us to shift the upper set of point and create this diagonal connection. So these are the 3 objects that I am going to use as our bars. Okay, so rigid bars. And now we also need the wires that we are missing. You see that the wires connect the upper vertex with the lower vertex with the upper vertex without any shifting. Okay, so in this case, for example, I can take simply a line and plug first and second branch of our tree. And well, let's disconnect here. So I'm going to now use our new definition in order to reproduce our Tensegrity structure. Let me also visualize once again our cables here. So you see that these are cables, while these are bars. Okay, so in order to have everything clear in the definition, I normally use a line container like this and plug all the lines that are, for example, cables in one container and all the lines that are bars in another container. Even if in this case it might seem useless, but this is in order to have a more clear definition. Okay, and then we start to give some elastic properties to this system. So as you know, these are straight lines. You go into Gold's line and take the length line component, and basically we apply the same goal to the 2 types of lines. So remember that these must be somehow elastic, okay? And these are going to be, let's say, less elastic, okay? Let's say so. So what I'm going to do, I'm going to tell the bars that their actual rest length is basically equal to the actual length of the lines that I am providing. Okay, so I don't parameterize the length input. I just say that I want this length to remain equal with a, let's say, quite a strong action. Okay, so instead of having 10, I'm going to set this to a 101 slider. Okay, which is a slider that ranges up to 1000. So normally I use 101 when I want to provide a very strong action to a goal. While as for the wires, remember that in Tensegrity structure, we are talking about pre-stressed cables, okay? So in this case, it's worth giving some kind of definition to the rest length as we did already. So we calculate the actual length of the segments that we are providing and then multiply this length by a multiplication factor as we want to only simulate pre-stressed elastic cables. Then I'm going to use a slider between 0 and 1 and leave it to 1 actually. So yeah, this is basically all this construction here is doing nothing because it is multiplying the actual length by 1. So basically we have the same effect as the lower length line, but this is a little more weak than the other one. And so now we have the proper physical properties for our lines here, and we can take a solver, we can take a toggle, we can take...
Carlo?
Yeah, tell me.
I just don't remember. I mean, why do we do length and multiplication and give one some like factor if in the end we have the same results? It's because then you can go lower than 1.
Exactly.
Yeah. All right. Sorry. Yeah.
Exactly.
That's
in case we change this to a lower value, we are applying some pretension to our wires.
All
That's
right.
the reason why.
Yeah. Thank
Okay,
you.
so you're welcome. So this is set to false, and now we have, oh, let me.
Sorry, Janka.
Yeah,
I have a question.
Yeah.
What's the definition of pre-stress and what's the difference with stress? Right?
well, it's pre-stressed is, well, it's just, well, let's think about this, okay? So if you take a beam, for example, like this, and you have iron bars inside the beam, okay? So if you, for example, place iron bars, I'm going to simplify with a schematic representation, okay? But if you place, for example, iron bars along this beam like this, like simple straight bars, then when you apply a load on top of this beam, this material here has some elastic properties, so it can bend like this. Okay, you allow some kind of deformation when you apply this load to this beam, because the iron bar that are the part of the beam that it's capable of absorbing this kind of load are basically allowing some deformation. This is something that can become critical, because if the bar can bend like this material here, which is concrete, basically cannot bend at all, basically. So you will be watching some fractures here in the beam. Okay, so that's why, for example, you use pre-stressed bar, which basically is taking the same bars, okay, eventually larger bar, and give them some pre-stress, which means you simply bend them like this. So you have a bent iron bar. Okay, and this is actually what it is doing. This, as this is a pre-stressed bar, it tends to go back to its linear configuration. Okay, so this bar is actually applying a vertical load, or a load which tends to be like this. Okay, and so when you apply the load, what happens is that this bar basically reabsorbs this deformation, because it can contrast this load here, and then can push up while this load is pushing down. So the combination of this thing makes your beam deform less than the actual beam if you were working with non-pre-stressed bars. So pre-stress means that you have a structure which is already subject to some kind of action, even when you're not applying any load, in order to give this element here, this beam, for example, more strength when you apply the load, and therefore less deformation, okay, which is critical for this kind of complex system, where you have a non-elastic material like concrete, okay? So that's why we use this pre-stress, let's say, name, okay? Now, in case of elastics or of wires like this, or cables, pre-stressing means only that these cables will tend to contract as soon as you release the Kangaroo simulation. Why? Because their length is going to be less than the actual length. Okay, so let's say, for example, that in case of elastic cables, which we are using right now, the consideration of pre-stress is this. We are using, for example, a line that measures, I don't know, 20. Okay, and what we are saying is that the rest length, let's say, is going to be 15. This is going to be the rest length. So this means that this elastic cable is actually it's in its elastic phase already, because rest length means that the cable is not going to compress or to extend, to contract or extend, while if you have a cable that measures 20, while its rest length is 15, it is already applying a force in this direction. So it tends to contract and to get back to this original rest length. So that's why we are going to pre-stress our cables, like decreasing this value here, okay? Why this is important? Because we will see now that as soon as we release the simulation, okay, as soon as we release this with a rest length which is actually equal to the actual length of the cables, this system will tend to fall down a little. Okay, so for example, if I reset and release this, oh yeah, of course I have to apply loads.
Giancarlo, the
Yeah.
force, isn't it in the opposite direction?
Sorry?
In the diagram, you draw 15 and 20.
Yeah.
If we have to arrive to 20, the force, the arrow, isn't it in the opposite direction? If
No, because this is the action that the cable is applying to the system.
Okay.
So if you well, let's say that I understand your question, but let's say that if you want to switch between 15 to 20, you have to stress the cable with a force like this in order to produce this kind of deformation here. Okay, this variation in length. But when you do this, and when the spring or the cable reaches this point, the cable itself is applying this load to this point. Okay, so we are interested in what's the elastic force applied, not the force we are applying to the end point of the cable, but what force is the cable applying to this point, because the cable wants to switch back to its original length. Okay.
All right. So it's the internal force in the cable.
Exactly. This is the pre-stress, okay, that we are going to consider. So, yeah. And any other question?
No, it's perfect for me.
Oh, okay. So I was missing the loads because Kangaroo works in a totally virtual environment. So if you don't apply any loads, there is no loads at all, not even gravity, not anything. So I need to apply loads to these points here. And eventually what I'm going to do in order to this thing can already work, okay? So if you see that if I turn on the simulation, if the bars are, let's say, elastic, but they are quite rigid because we are giving a very high value for the strength, okay? And also, the elastic cables are in their actual rest length, so they don't tend to contract. But if I take this and contract this, you see that the system is reacting, okay? And the reaction is that the bars, which are the interesting elements in this case, are starting to twist, okay? So think about that. These basically these diagonal lines here are the bars. Okay, so you see that we already have the twisting occurring, but we are working in a totally visual environment, as I was saying. So if you take a look from the front viewport, you see that the system also raised up to, let's say, 1 unit upper, because there is no anchor point, there is no vertical load. So let's see how this system would work in real life. Okay, so what I'm going to do, I'm going to take this, set it back to 1, turn off the simulation and reset it, and I'm going to apply loads and also anchor points. So our anchor points are going to be these 3 points. Now, this is not exactly correct. When you work with a tensegrity system, there should be no anchor point because the system is self-bearing, okay? So there is no need to anchor it somewhere. But in our case, I just want to point out how the pre-stressed condition helps the system to maintain its stability, okay? So that's why I'm going to use anchors. But in a real tensegrity structure, there should be no anchor point, okay? That's by definition. But anyway, we are going to work with real life structures, so there is always some anchor point. I think, in my opinion, this doesn't affect the general behavior of this structure. This is still a tensegrity structure, even if it's anchored at 3 points. But if you want to be extremely precise, you shouldn't have any anchor points. So if you want to simulate a real absolutely correct tensegrity structure, you should insert this floor here in order to avoid that these 3 points will fall down below XY plane, okay? So later on, we will simulate it with this in order to free the tensegrity system from any anchor point. But for now, I want to stress it a little more. So let's take a look at what happens when I use anchor points. So we have the points here. Layer 0, 0 or branch 0, 0 is the lower one. So I'm going to anchor these points to the ground like this. And I'm going to go to set the goal objects as well. And I also need some loads, and I will apply loads to the upper points, which is 0, 1. Yeah, okay, it's 0, 1. And I want to apply a force vector, which is basically minus x. I don't care about, well, actually, yes, I do care about the intensity in this case. So I'm going to use a z vector with a negative values between, let's say, minus 10 to 0. Okay, so let's see what happens when we start playing with this load. And then later on, we will switch to a floor instead of anchor points. Let me place it like this. And let's plug the load to this system. Okay, so now if I release the simulation, okay, you see that there is actually no pre-stressing, meaning that our cables, which are these ones here, tend to maintain their original rest length, but they are weak because their strength is 10. Okay, so when I apply a load to these, the fact that they cannot basically, they are not so strong. If I increase the load, you see that the structure tend to collapse. Okay, and if I take a look at this, you see that things have become like critical in this case. Keep in mind that Kangaroo cannot calculate these collisions here because we have not programmed this kind of effect. But later on, if you want, we can give thickness to these poles here and apply some collision in order to make things more realistic. But anyway, this is already collapsing. Okay, you saw that there was some kind of point where the system deformed quickly, okay, and badly. That's what's basically the point break, okay? So if I reset this, you see that as I decrease this, there is some elastic deformation, okay? But when I reach a value, like for example, here, you see that this is already collapsing. Okay, so this means that we already reached the critical point. You see that once we reach that point, we are no longer in the elastic phase of the system. So even if I eliminate the load, the system is not capable of going back to its original configuration. This is totally symmetric. You see that the beams, or sorry, the bars are intersecting at the centroid of this prism, basically, but this is not a good result. Okay, so let's go back to our definition. Let's see what happens if I give some pre-stressing to our cables, okay? So if I run the simulation and start applying a load, you see that this load tends to deform the system. We already have some twisting, okay? Very light twisting. But if I do this, you see that this thing is becoming more and more strong in terms of elastic action, because the springs are basically stressing more, and then because they are pulling each of these vertices here, not the lower vertices because they are anchored to the ground, but the upper 3 points are being pulled by 3 springs at a time, okay? So basically there are 2 springs that are pulling this point here horizontally towards the other 2. So if I apply a stronger load now, there will be a double action from these 2 springs here that will tend to avoid additional torsion. So if I do this, you see that the system is more capable of resisting to the load. Of course, there will always be a point break, but you see that we are not reaching the point break even with a very strong load that was basically making our system collapse, okay? So if you have pre-stressed cables and you apply a load, the system tends to deform, of course, but it's harder for the system to collapse. And also, when you have pre-stressed cable, more load gives the system more stability, okay? So you see that the system tends to, let's say, bounce around when you use lower values for the load, and tend to stabilize quicker when you apply stronger loads. Okay, so that's exactly the principle of tensegrity structures. Okay, so you see that in this case, as tensegrity structure have a big elastic component in their behavior and their dynamics, then Kangaroo, I think Kangaroo is a very useful tool to simulate this kind of behavior. Okay, so Kangaroo is I wouldn't say it's perfect, but it gives you quite a good approximation of how a tensegrity structure works in real life. Okay. Of course, in this case, you might want to also work with real life values, but remember that you also have the undesired side effect that the simulation becomes extremely slow. Okay, so you see that, for example, just giving a little pre-stress to our cables, the system can bear quite a huge load if compared to the previous one. Okay. Now, you see that also it also works in terms of non-progressive application of loads. So once you know what's the factors that you must use, you can also release the system quickly, and it tends to find its own equilibrium phase. So what you might want to do after this simulation is eventually isolate the items, the different items, in order to give them some preview, because else it's very difficult for the deformed system to understand which are the bars and which are the cables. So I do recommend that you do this. There are mainly two types of goals in Kangaroo. The goals that provide some geometric preview, and goals that do not provide geometric preview. Okay, so is there any question? I heard a microphone.
I mean, I
Yeah.
didn't speak, but I can just ask. I mean, it's difficult to me to have an idea of 0.95 is like to
Yeah,
have.
it's a scalar. It's a scalar value. There is no meaning for this, but you can also do things like this. You can calculate, for example, the actual length. Well, sorry, we already have it, and then this is basically a number, and this number is going to be a physical value, okay, which is basically saying you have, let's say, this original length, and you are saying that your springs tend to contract from 30.6 to 28.8, more or less. Okay, so if you want, you have access to numeric values, and you can also calculate, for example, what's the deformation. You can use this information in order to visually show what are the cables that are contracting more or less. We will do this in a while. But anyway, you have access to this information, and also remember that you can work with real life strengths. Now, in terms of let's say physical properties, um, you must think, for example, that these cables here will be eventually made up of a real material, and that real material, well, it's very unlikely that you can have a let's say a significant amount of contraction of an elastic body in real life. Okay, so basically what we are saying is that unless you work with lycra, for example, if you imagine this was a thread of lycra, one single thread, okay, and you, in order to connect this endpoint to this endpoint, you stretch this thread very much and anchor it to this point and this point, and do the same with all these cables here. So one single thread of lycra, pre-stressed, extremely pre-stressed, and you should basically calculate or simulate all of these using lycra physical properties. Okay. Now, I always remember this is very good if you want to know how the system will work, but I do not recommend, especially when you work with sorry, with extremely elastic bodies. So sorry, guys. That you don't rely on Kangaroo as a precise tool. Okay, so sorry, let me grab a glass of water, please. Yeah, okay, I'm back. Um, So basically, I wouldn't rely on Kangaroo for a realistic simulation, but you can simulate some kind of equilibrium between the values. So your question, let's say, forces me also to another consideration. We are not working with a real load. Okay, so we are not defining a precise relationship between the elastic force and the real load. So it's totally scalar here. There is no actual values being considered. So it's just an equilibrium between the forces that we are using right now. So it has no meaning. So 0.94, it's meaningless as minus 10. Okay.
So minus 10 is not minus 10 kilonewton.
No, absolutely no, because we are not working with real elastic strength. We are saying that this material has a strength of 10, but we know that the weakest material, like rubber, for example, in terms of elastic properties, has already a strength of 10,000 maybe. Okay, so there is actually no physical meaning for this simulation, but the fact that it is proportional to what happens in real life. So what I get from this simulation here is that if I take solid bars and elastic cables, eventually pre-stressed elastic cables, I see that the system is capable of bearing some load. What's the amount of this load? I'm not simulating this because I'm not working with real life values here. So if I work with real life values and I want to use, I don't know, cotton, I should use the elastic equation that I shared. I think, yeah, it's available on my website. And it's that cluster that we saw in the first session. So I have to use it, and I have to provide the result to this, and I have to adjust all the values accordingly. So in that case, I am able to work with kilos and newtons and so on. Remember, don't use weighting, just use direct definition for these values here. And eventually, I will be also defining, for example, what's the property of the rigid bars, because I can no longer work with a strength of 101. I should increase this to very, very, very high values. And I have also to tweak the strength of the anchor points, else this system is going to be able to move. So yeah, in that case, you can still have a realistic simulation, as I was saying before, but the simulation tends to become extremely, extremely slow. This is actually something that I've been doing with a company from Hong Kong. They are building some furniture with this Tensegrity system, and we must create realistic simulations. So in that case, simulations are running very slow. Like, for example, you run the simulation and you go and eventually have a quick snack or eat something, and then you go back and the simulation is still moving. Okay, so you have to wait a lot of time for the simulation to get to an equilibrium state. So in that case, yes, you can do it, but it's not convenient, okay, for this kind of preliminary simulations. Like,
Giancarlo, is
yeah.
it something you can share from that? I mean, not at the moment, just to have an idea of how many parameters, how will it look like this work you are doing with
Let me double check. I will.
Yeah.
Actually, I have an NDA agreement with them, but eventually I can. So I cannot share exactly the system, but I will share with you eventually a screenshot of the forces and goals definition, so you have an idea of what happens.
Exactly.
Yeah.
Just to understand how it will work, not that we will use, but just to have an idea.
Yeah, but you will see, for example, that later on, when analyzing and discussing a different Tensegrity system, we will also be working with other goals that becomes necessary, okay? Because the problem in this case is that we are simulating, for example, rigid bodies like these bars here as elastic bodies. So we have to make some adjustment to our definition in order to have this body maintain their rigid aspect, even if we are working with an elastic system. Okay, so we are only considering soft bodies in this case, but we are saying that the rigid bodies are extremely rigid soft bodies. Okay, so this brings us to a more complex definition in Kangaroo in order to maintain the balance between rigidity and elastic system properties. Okay, so but we will see this in a while, because when I will share with you the screenshot, you will see that there are several loads in the definition. Okay, much more than these. But anyway, so in this case, what I wanted to do next was to substitute the anchor points with the floor. Okay, so say I no longer want to work with the anchor points, I want to work with a real tensegrity structure, and I'm going to use the floor. Now, in order to use the floor properly, we are applying a load 10 to 3 points, so it's globally 30 in this case, and the floor has a strength of 1. So if I run the simulation here, you see that the system, yeah, it's working, but the floor is not capable of containing this, so the system starts to do something strange like this. Eventually it will flip because of the twisting, but anyway, I don't want this to happen. So the floor, remember, consider the floor as a physical constraint. Either it is present or not. So if it is present, its strength must be equivalent, for example, to the strength of an anchor point. So anchor points have 10,000. Now, if we apply 10,000 to the floor, this can have some undesired effect, okay? Because the floor is something that it's different from the anchor point. So the anchor point is something that keep one point in its original position with a very high strength value, okay? But this means that that point cannot move at all, okay? While the floor is, actually you can think about the floor as a collision plane. Okay, so when the system touches that collision plane, the plane acts with a force which is opposite from the force that it's actually pushing, for example, the point down. So you are saying here that the system must bounce against the floor with this kind of strength. Now, this can make your system extremely unstable. So the system starts to vibrate eventually and start to bounce around when you do something like this. I do recommend that you take a look at the forces that you are using and eventually increase the strength of the floor to a value which is capable of simply not letting points pass through the floor plane. Okay, so you see that this system will always work even if I consider very some kind of smaller values, like this case, for example, instead of 10,000, 1,000. And if we go into the front view, you will see that we are already a little lower than the ground plane. Okay, you see this. But I do recommend that you accept this kind of very small error, let's say it so, because at the scale of the object, it's basically irrelevant, okay? And you see that things become like extremely visible when you reach values like, yeah, for example, like this. We are applying a load of 30, okay? So that's why you see that things becomes, let's say, visible when you reach more or less that value. Let me change the range of these between 10 and 100, which is more than enough for us in this case. And so we will be able to see that the system starts to be in equilibrium at 30. And then if we decrease this, we have some kind of extremely visible error here at the base, okay? So if you give 100, I think it's more than enough for having our system work properly, okay? So you see that you can avoid anchor point and create a real tensegrity structure, which is basically subject to gravity. And the fact that these bars are not moving and are not falling is only due to the elastic cables that are also connecting the base triangle, okay? So this is actually a real elastic system, or tensegrity system, sorry. And now, what I was saying is that when you work with Kangaroo, you want to isolate or separate different types of elements after the simulation in order to work with them, what I do recommend is to separate the goals that have some geometric aspect and from the goals that do not have any geometric aspect. So for example, this load has no geometric meaning. It's a force, it's a vertical force, okay? Also, this floor here is basically a collision. It has no geometric representation, okay? But the springs, yes, they do. Okay, so you can let's say disconnect all the wires from the bouncy solver, and also let me turn off the preview. Oh yeah, I must reset this. Okay, so you see that if I plug the load to the goal object, I have no preview from the Kangaroo solver. Okay, if I plug the floor, I have no preview. If I plug the anchor points, I have no preview because this is a constraint. Okay, but if I plug these and reset it, I have lines. Okay, if I plug these and reset, I have lines. Okay, and each line, each spring has 2 points, which are the endpoints. These are the particles or vertices of the simulation. So these points will come out from here. You see, we have 3 lines here coming into the goal object, and you will have in output, you will have 3 lines. And in B, you will have vertices as list, which are all the particles, which are all the endpoints of the springs that we are considering. Of course, if we plug the anchor point and reset, vertices will have 6, and output will have null, null, null plus lines. So these 3 nulls come from goals that don't have a geometric preview. Okay, so I would recommend that in order to work with the output from the bouncy solver, you do something like this. You organize the input of the goal objects. Okay, so for example, I would use something like an entwine, okay, like this, where I plug into branch 0, 0 all the goals that don't have any geometric preview, or all the goals that do have geometric preview. For example, I'm interested in working with the springs, okay? So I plug this and this into branch 0, 0. Okay, and then I plug all the goals that don't have any geometric preview into branch 0, 1, like the loads, actually the floor. I don't want to work with the anchor points, and that's it basically. So I get a tree as a result. I get rid of the unused branch, and I get a tree which contains these goals into 2 separate branches. Okay, and then I plug these into goal objects. This is a feature that has been introduced in Kangaroo 2, because in Kangaroo 099, the forces, you basically must provide forces into in a list, a data structure. Okay, so in that case, for example, I normally tend to use, when I work with 099, I use a merge with a flatten at the output. So I plug all the forces into data 1, data 2, and so on, and then I flatten the result and pass it to the solver. Okay, because you can see it like here. If I grab the Kangaroo solver from the previous version, force object asks for force objects as list. Okay, now in this Kangaroo 2, there has been this implementation where goal objects accept trees, and it's convenient to provide trees, especially if you do this kind of differentiation between the goal. Okay, so when you take a look at the output from the here, you will see that eventually you can more easily, let's say, handle this output here, because you see that you have here a data tree with 16 values, but they are divided into 2 branches. The first one is containing 12, and the second one is containing 4. Okay. Now you see that the output, even if you plug here a data tree, the output still provides a list of values. Okay, but you see that, let's take a look at this with a panel. You will see that the first branch of our data tree here contains 12 values, and they're all springs. So we already know that they convert into lines in Kangaroo. And then the second branch contains 4 values, and they are all non-geometric goals. So they convert into null in Kangaroo. Okay. So if we take a look with another panel to the output, you will see that we have 12 lines And then we have 4 nulls. So even if we have a list, values inside that list are maintaining the same order that they have in the data tree. So it's like this data tree being flattened and providing us to do this list of values. So what we can do right now is go into set tree and eventually match the tree. So if I take, for example, let's say I plug this into tree and plug as a guide, I'm going to plug this here. Now this becomes red because it asks for a tree. Okay, so if I graph this, you see that there is basically no let's say advantage. Okay, so this is still giving us an error because the 2 trees must have exactly, you see here, equal number of paths. Okay, so basically what I'm going to do, I'm going to use a let's say trick in order to turn this into exactly the same data structure as this one. Okay, so I can explode, sorry, I can use tree statistics in order to understand what's the structure of our initial data tree. Okay, and then I'm going to apply the same structure to the output here because I know that the data are sorted in the same way as the original data tree. So what I need to do right now is take these values and give them the same structures that we have here. So eventually I can use a partition list like this, where what I'm going to do, I'm going to create branches where size is actually correspondent to the length of the branches of the original data tree. So if I plug this, now what I have here is exactly the same data structure as the original one. Okay, so in this case I can solve this problem with a simple partition list and the tree statistics. So the thing is that once you have this, you can explode the tree and you have access to your geometry into branch 0000, okay, which is the first branch. You can also simplify this tree in order to have just a one index for your 2 branches here. But anyway, in this case, we have we have lines here and all the null objects here. Now, if you want, we already talked about this. You can also use a simple clean tree and clean the output and get rid of nulls, because remove nulls is set to true. So you already have all the lines here. This is also valid, but in case you are working with more complex simulation, you might want to separate several data types. So for example, if I clean tree like this, I will have all the lines together into this list. But if I'm also working with meshes, for example, for a 3-dimensional simulation, and I simply clean trees, I will have lines and meshes inside this. But if I work with a controlled data tree initially, so let's say I plug all the goals that provide a line as a geometric output into 0, 0, all the goals that provide meshes into 0, 1, and all the goals that don't provide any geometric preview, I plug them into eventually a 0, 2, then I know in this case that 0 will contain lines, 1 will contain meshes, and 2 will contain eventually null objects. So if I do this, I am able of separating several types of data according to the different workflow that I want to actually adopt with any type of geometry that is involved in the simulation. Okay, so this is very convenient when you have extremely complex simulation involving several data types. Okay, else if you want just to work with lines, you can work with a clean tree in this case. Okay, so what I want to do right now, I have the lines here, and let's separate, for example, the let's separate the bars from the elastic lines. Now I am working with a simple data tree here where I plugged all the bars and all the springs inside the same input, okay? But once we know how this system works, what we can do is basically add another input here, and use this second input for the null object. So I shift all this cable here from 0, 1 to 0, 2. I disconnect the bars from 0, 0 and plug them into 0, 1. Okay, so we have springs here, which are our elastic cables, and the bars are now into branch 1. Now, I don't care about the fact that this is getting orange, because this is a warning saying that this data tree has more than 2 branches as an output. So I should add another branch, another output, but this is the null object. And here we have 3 lines, which are the bars, and here we have 9 lines, which are the elastic cables. Okay, so you see how easy it becomes to work with the output once you create this kind of separation between data types. Okay, instead, here we still have the same list of lines where well, actually it's impossible. Well, it's not impossible. We should do some trick in order to isolate the bars from the springs. Okay, while in this case, it's very simple. It's the one output. So bars are here.
Is it a quick way to isolate from clean trim?
Well, actually,
it's a long process.
No, it's not a long process, but you have to make some considerations on the system and on the deformation eventually. Even in this case, you can also, let's say, rely on in which order you plug your grasshopper wires inside this entwine. For example, even if here we have separated the springs from the bars, 0, 0 from 0, 1, when you pass all this information to the solver, we already saw that in the output, the order in which the lines appear in this list, it's absolutely the same order in which they appear in this data tree. Okay, if you don't consider the branches, the first lines here will be the elastic cables, and the second lines in the data tree will be the bars. Okay, so when you take a look at this output and leave the nulls aside, you will have the first lines will be the cables, the elastic cables. You see up to the 9th value, which is index number 8. And then you have 9, 10, 11, which are these 3 lines. These 3 lines are the bars. Okay, so if you want, you can also, it's very easy actually to isolate these 3 lines, but also I wouldn't recommend to do this like this. I wouldn't use a list item, for example, because it depends, everything depends on the order. If you change something here, the same list item will give you access to different values or different lines. So you can do some geometric consideration. For example, let's analyze our system, which is this one. And for me, the more important characteristic is that the bars are diagonal, while the springs are basically connecting vertices, or either vertically or horizontally. Okay, so it's evident that the diagonal bars are longer than the springs. So you might want to make some certain workflow in order to isolate the bars. For example, I would calculate the length of these lines. The geometric length of these lines, and eventually you will see that what would be the right criteria. For example, in this case, I wouldn't take the longest lines. Okay, this is very simple. Okay, you might say, okay, so I see that as they are diagonals, I take the longest lines, and those would be the bars. But it's not like that, because it depends on the system. Now we are working with a very simple system where eventually the longest lines are exactly the bars. Okay, but if you work with a very complex tensegrity structure, that's not a good rule. So my consideration would be, okay, there are elastic lines and less elastic lines. So what happens to the less elastic lines? That their length will change less with respect to the elastic lines. So what I could do eventually would be something like this. If I take a flattened tree, I'm looking for a safe way of detecting the bars. Okay, so if I take a flattened tree, I have all the lines here. Flattened tree, not of this entwine here, but of the lines. So before plugging them to the goals, I already have a tree of lines, which are the elastic lines, and a list of bars, which are these lines here. So I plug them exactly like I'm plugging them in the entwine. So I plug here elastic lines and non-elastic lines. So I am plugging this kind of tree here. You see 0, 0, 6, 0, 0, 1, 3, and 0, 1, 0, 3, which is exactly the tree that we are getting from here. The first branch contains 6, 3, and 3. And here we have 6 and 3, and 3 lines here. So when I do this, I have exactly the same order that I get after the clean tree. Okay, so if I do this, you see that I get exactly the same order. And as the system is not running right now, you see that the lengths are absolutely identical before and after the simulation. Okay, so how do I detect the bars? Well, actually, I would calculate the length of the lines before the simulation. Okay, this is before the simulation, and this is after the simulation. And then, for example, I would do something like a division, where I divide these two lengths by the other. And so when I have a result which tends to be 1, it means that the line is not deforming, basically. This means that it is rigid enough. So it's a solid bar. Okay? So during the simulation, if I take a panel here, now I get a list of 1, basically, because there is no deformation occurring in the system. But when I run the simulation, you see that there will be some deformation here, and then there will be 1.00, which is more precisely equal to the original length. So this means that these are the bars. Okay, so you can perform this kind of analysis and use this method, which is basically a comparison between the undeformed system and the deformed system. This is something that you can also use in order to perform some kind of visual analysis. For example, let's do this with another example, and then we will go for a break. So for example, let's say that you have these values here, okay? And we want to visually detect which are the stressed objects, okay? So this value coming out from the division here is an expression of the deformation, basically. So you see that there are some lines that are deforming more, 1.034, and some lines are deforming a little less, 1.027, and some lines are basically deforming very, very little, which is 1.005, okay? So if I take a custom preview, and I want to visualize these lines which come from the deformed system, okay? I want to give them a custom preview where the color depends on the stress, okay? Represented by the deformation. So what I'm going to do, I'm going to use, for example, a gradient, okay? And I want this gradient to be something like from color left is going to be white. Color right is going to be white as well. So we have this gradient between white and I'm going to use plain red. Okay, like this. So I have a gradient between white and red. So when I see, for example, that this value becomes larger, like 103, I will get red. And when this value is closer to 1.005, it will stay white. Okay? So what I want to do, I want to translate these numbers here into a color. And so parameter is going to be the value that I want to place inside this gradient bar. Okay? And lower limit and upper limit are basically the extremes of this list of values. Now, if you have plugins like Heteroptera, for example, you can use simply this min-max component here that gives us directly the minimum value and the maximum value of this list. But if in case you don't, you can use, for example, the function that is called bounds that basically creates the range that contains all these values here. So this range would be between 10055 and 10344. Okay, and once you have these, you deconstruct the domain. So you have access to the start value, which is the smallest value, and the end value, which is the largest value in your original list. And then you plug this to lower limit and this to upper limit. So in any case, you have access to the lowest value and the largest value in your list. Okay. If you have Heteroptera, you can simply grab a min-max component, which is quicker. And yeah, and then we use this color as the material. So you will see that the bars are basically white because they are receiving less deformation, and then everything else starts to become reddish according to the deformation that it's getting. Okay. So yeah, basically this is a visual way of isolating or differentiating the bars from the elastic cables. But this is useless if you want to make some further action on these elements, because they are still into one single list. Okay, so they are not separated into two different sets of objects. Okay, this is some visual representation. Okay, so if you want to separate them by bars and cables, then you might want to work with Explode Tree because it is more practical. Okay, or eventually use this result here in order to create some kind of true-false pattern, like for example use similarity, where you evaluate if this index of deformation here is similar to second number will be 1, and using a threshold. Okay, so if we want to work with this, we have to consider the proper value for the threshold. Threshold is expressed in percentage. Okay, so you see that it ranges between 0% and 100%. So 0.1 means 0.1%, but we know that our bars are basically, let's say, these. So you must lower the tolerance, or yeah, basically it depends on how you want to see it. Lower the tolerance value or increase your tolerance. I don't know. You can see it from your perspective, but anyway, lower the tolerance value down to well, basically 1/1000, because else you are not capable of detecting this kind of precision here. So in this case, you might want to use a threshold between 0.001 up to 0.1, which is precise enough. And in this case, eventually you will get some true. Not even in this case, we have to lower it. So you see that it becomes very boring to do this kind of analysis. Okay, that's why I do recommend that you start working with your well, actually, you see that even in this case, it is not detecting the value, but you can also work with the absolute difference. You know, it's boring and it's tricky to work with this method here, because it depends on the system and the deformation that you are applying, and also to the parameters that you are using. Okay, so you must tweak eventually this every time you run the simulation. While in this case, there is no need to tweak anything, because it depends on how you plug your cables or your bolts inside this entwine. So you already know exactly where are the beams, or sorry, where are the bars and where are the cables. Okay, so I do not recommend you work like this. Do something like this comparison here before and after the deformation, in order to give some visual representation, but always rely on this method to isolate your elements properly. Okay, because it is quicker and it doesn't depend on the deformation and on parameters. Okay, made a quick change to the definition. So I am repeating the same scheme from the first session, where we have my original scripts here, and on the right some exercises in order to deeply analyze what is done here on the left, with the same jump that we already saw in order to connect the exercise properly with the script on the left. And I have also organized and put some note here to remember what was the importance of some steps, like the entwine here. Here I specified that you need the heteroptera plug in order to use this, and this is the name of the function min max. This substitutes the bounds and the constructor min. All the rest is pretty straightforward. And I'm also leaving this note here on pre-stressed in order to remember what are we doing here with these pre-tension cables. Okay. So as there is no further question, I will turn this off, disable all this part here, and move to the next one. Now, the next one is a replica of a system that was created in an exhibition last century. This is basically a set where the poles or the bars are these little diagonal lines here. And then there is this large element, which is another rigid bar, which is basically suspended to this structure. Of course, in this case, for example, it's evident that this cannot be a totally free Tensegrity structure, because in order to have these poles here, these bars stabilized, basically, this cable here must be anchored to the ground. This bar here must be anchored to the ground here, and also for the remaining two parts of the system. Okay, so this system is not free to move around. It's anchored to the ground in these 6 points here. Now, this I will not repeat the geometric consideration for building the elements of this system. I will only point out how was this system was created. It's pretty straightforward. It's just a standard polygon. You see that there are 3 different polygons with different radius. The first radius defines the anchor points on the ground of these bars here. The second defines the upper end points for the bars. And the third polygon defines the anchor points of these elastic cables surrounding the structure. Okay, so that's why you see these 3 triangles. Of course, you can change the system accordingly. You see that I think I already told you, but Kangaroo doesn't like real-time geometric system editing. So if you do this, you must also reset the simulation in order for it to update to the new geometric system. And as well, actually, the first and last triangle are actually defining the anchor points properly in the exact position. But I also needed these upper vertices here, so that's why I exploded or calculated the discontinuities, which are the vertices, and then moved the vertices of the mid triangle up with this move unit C. And I used this entwine here because I needed to create the same set of displacement motion vectors for these 3 branches here. And so I only want to move the mid branch using this slider here. Okay, so this defines the position of the upper endpoint of our bars. Okay, so let's undo this once again. So I am back to the original configuration. So here's the final set of points. Okay, 2 are going to be anchor points. 1 is going to be the simply the endpoint of this bar, and also the endpoint of this cable here, and also an endpoint for this cable and this cable. Okay, so Once I move this point up, you see that this point comes from the discontinuity. So there are three points belonging to one branch. And these 3 points are grouped by polygon, by triangle. But I want to create this bar and this cable. So I needed to connect not the vertices of each polygon, but the vertices that are correspondent between the different polygons. So I don't want to connect by polygon, I want to connect by correspondent vertices. And then I flip matrix. So you see that in this case, we have 3 sets with 3 points each. And here we have 3 sets with 3 points each. But now the points are sorted in a different ways. We can take a point list with a slider here, just to make this number more visible. Okay, so you see that these are points 0, 1, and 2 of the first triangle, 0, 1, and 2 of the second triangle, and 0, 1, and 2 of the third triangle. So, for example, as I want to create this connection, I want to connect point 0 with point 0 with point 0. But these point zeros belong to different branches. Flip matrix, what it does this. So it is basically saying I am grouping these vertices by their correspondence. So all the vertices that lie on the same side of the structure are now grouped together into one branch. And therefore, if I connect them with a polyline, I get this polyline here, this polyline here, and this polyline here. If I don't do this, if I don't flip the matrix, I get back to the triangles. Okay? So that's why this flip matrix. And here, what I'm considering is that the midpoint here, which is this one, must be used to create these lines. Okay, so what I'm doing here, I'm taking the flip matrix set where the, let's take a panel here, where what I need to isolate is the point that lies at this height here. Okay, so I took a list item with index set to 1, because this is giving us the point with index number 1 per each branch of the tree. So we have these 3 points here, separated by branches. And then I am creating a different point. I am moving up the center point of my structure, which is this one, is the center of the polygon. I am moving it up to a certain height because this would be the base, the start end point for our vertical rigid bar here. Okay, so I move this thing up. I create also a straight line SDL vertical line with this extension here. And I also take this displaced point here as the other endpoint for these 3 lines. Okay. Now, these are the basic lines. Okay, so the bar here, the elastic cable here, and this elastic cable here. Now, we have a problem. This elastic cable here is not connecting this endpoint with this endpoint or this endpoint, because in the original structure, this cable connects to more or less half the length of the line, or 2/3 maybe. I don't remember exactly, but I will share with you the picture. I will take another picture frame and place it here in order for you to have the exact reference of what I'm talking about. I forgot to do this, sorry. But anyway, the fact is that this elastic cable is not connecting the end points of this bar. Okay, so in this case, we need to define an anchor along the length of the bar. Now, this will lead to the real consideration for this particular tensegrity structure, because until now we have only worked with cables connecting the endpoints. Now we have something weird happening, which is this midpoint, more or less, along the length of one rigid bar, and we must understand how to deal with this. Okay, because this is not so obvious. So what I did here was create a point on curve, which is defining this connection point along the line. okay? And then I use this point on curve here to create these other wires here, these other lines, which would be our elastic cables connecting to this point, okay? And that's it. This is basically the geometric system. So we have basically bars, remember, one container for rigid bars, where I plug let's say, I have created the polyline. We left at the polyline. I am exploding the polyline in order to have access to its segments. Okay, it's 2 segments per polyline. And then I take segment number 0, which is the first segment of the polyline, and use it as 1 bar. The second segment, which is this one, is going to be 1 cable, elastic cable. Okay, so you see it's present here. And I need to plug the second segment of the polyline, as well as the segments that connect the base of the rigid body here with the top of this rigid bar here, and also the other one, which is connecting the endpoint of the bar here to the midpoint or the inner point of the rigid bar, vertical rigid bar here. So all of these lines are elastic cables. Now, as I told you, this system needs some anchor points. Okay, so you see that here we have an anchor container, which is basically taking all the points from these initial discontinuities, displaced discontinuities for our system. Okay, and it's just deconstructing these points in order to have access to the z value. And what I want to do, I want to use only the points that have z equal to 0, because they lie on the ground. These are going to be our anchor points. And then I call pattern, and then I get rid of the higher point here, and only consider the points that are lying on the ground. And I convert them into anchor points. Okay, so here they are. And I want to apply loads, as always, and I need to apply these loads to the points that are involved in this simulation. So basically, I'm applying a load to all these points here, despite the fact that we have anchor points here. Remember that anchor points are way stronger than any other load or any other force applied to the system. So even if I apply a load to this, it won't be capable of moving the anchor point from its original position. So when you work with loads, you can simply apply loads also to anchor points. They won't be affected. Now, this is not a general principle in Kangaroo. For example, you might not want to apply, for example, some collision actions, like, for example, sphere collide to anchor points, because this is something that eventually could crash your simulation. Okay, so what I'm doing here, I'm considering simply the whole set of points, including the anchor points, to apply loads, because this is something that Kangaroo allows, but this is not a general principle. Okay, and I also need to apply a load to these 2 points here, which are the extremes of our vertical rigid bar here. And yeah, basically that's pretty it. I should also apply, well, actually I'm considering all the points. Yeah, actually all the points. Now, I'm not applying a load to this point here for one particular reason. This point yeah, it's part of the system actually, because it's the endpoint for these cables here, but it's not part of this rigid body here. So in this system, we give preference, for example, to rigid bars in terms of applying a load, and we rely on cables just to maintain the whole structure in place during the simulation. So I'm not applying a load to this point here, because it would be basically useless. Okay. While what I'm doing here, it's a particular thing. You see that there is this other point container here, which is actually containing the endpoints of the vertical bar and the midpoint that we are detecting with the point on curve. You see that the endpoints and point on curve are connected to this one. Now, this is the new aspect in this simulation. Let's see how to deal with this. Because, well, bars are actually our length line, our springs, which are more stiff, let's say so. Okay, so we increase the strength to 100, let's say. Or I will eventually use a 101 slider. But anyway, then there are the cables, and the cables must have an elastic property with some pre-stress, which is represented by a multiplication factor, which is smaller than 1. I will leave it to 1 for now, and then we will tweak these values during the simulation to see how they affect the simulation. Then there are the anchor points, which are simply these points here. And then there is the load. Okay, so we can tweak the load and give a value of a negative value to this, like to simulate gravity. Okay, and then there is another particular need, because we need this thing here. It's a rigid body, well, let's say a spring which is very stiff. So we can consider it like a rigid body. Okay, and we are trying to restrain the movement of this rigid body by anchoring or by grabbing one of its endpoints and one point along its body. Okay, but this point along its body is not coincident with the endpoints. So what would happen during the simulation is that this is a particle which is disconnected from the particles that represent this rigid bar. So these elastic cables here during the simulation will tend to contract because we are going to decrease the multiplication factor for the rest length. So as they contract, this point will not be anchored in any way to this rigid bar here, because Kangaroo doesn't know that this particle belongs to this body. Okay, so this body will start to move down along this bar here because of the contraction of these three springs. But there is no force that is going to maintain this point on this bar. And therefore, this bar will not be connected to these three springs here. And it will be able to fall down in either way in 360 degrees around this point here. So what I'm doing here, I'm considering an additional goal, which is called collinear. And collinear are some goals which are in this group here, which is the co-group. You see, there is co-circular, co-linear, co-planar, co-spherical. Okay. Now, why I'm using this? Because what I want is these 3 points to be aligned during the simulation. So this will force this body here, basically this bar, to have its endpoints aligned to this midpoint here. This is a previous a schematic simulation for this system. Of course, this is not perfect. We are going to tweak it a little more in a while, okay, in order to produce the desired result. But anyway, this is the first step. So we are saying that these 3 points must keep their collinear relationship during the simulation. Okay, so when I reset and run the simulation, and I start to tweak the values. Okay, for example, I start to apply a load to this, like this. You see that the system is already reacting. Let me turn off the preview of this thing. Oh, okay, it collapsed, but I was expecting this. So what's happening here? Let's take a look at this collapsed system. Okay, you see that the anchor points, well, basically they stay untouched. Okay, but this is normal. Basically what's happening here is that we are working with absence of pre-tensioning for our cables. Okay, so they can stretch, they can expand during the simulation, and the fact that they can expand means that this bar here and this bar here are not controlled by the system. Okay, so when we apply a load when the system is already pre-tensioned. Okay, so first of all, I give some pre-tension to this. You see that this is actually contracting these springs, not these on the sides, because their extension is controlled by these 3 here at the center and these 3 here at the bottom, at the top. Sorry. Okay, and then I can apply a load. And I will apply a load to this. You see that the load is being applied to the vertical bar. And this makes this bar, let's say, move along its vertical axis, because these 3 points are kept collinear. Okay. Now this bar can no longer fall down aside because this point here and this point here are receiving a load. The fact that this point is receiving a load could make this bar fall aside, okay? But as this point must be collinear with this, which is kept in place by 3 springs, and this one, which is kept in place by 3 springs, these 2 points are necessarily on the vertical direction. And therefore, this point is kept vertical due to this collinear goal. Okay. Now, this is not exactly, let's say, correct. Okay, because in Kangaroo, when you apply springs to a point, that point should be a particle of your system, also for the rigid bodies. So in this case, what we should do in order to have a real tensegrity simulation should be to split this line into 2 parts. Why? Because if you take a look at this, if I apply a load, I have this rigid body here sliding up and down. But in the real life, if you anchor 3 cable to a specific point along this body here, this point will also move up and down if this rigid body moves up and down. But you see that the rigid body is free of moving up and down, while this point here is not moving, is not following the body, okay? So this is not correct. And in order to do this correctly, what we must do is some tweaking. And I'm not going to do this here. I'm not going to change this system here. I'm going to do it in a copy of it. So
Giancarlo,
yeah, tell me.
how much is the strength in the anchor point?
10,000 by default.
All right.
Okay, so I'm moving here and I'm going to do some tweaking to the system in order to see what happens when we take into account that this point must be basically bound to this body. So if the body falls down, this body must move down with the body, okay? So that point is defined by this point on curve, okay? So instead of doing this, like using a point on curve, what I'm doing right now is this. I am substituting this point on curve. Well, actually, I can also leave all the rest untouched. So I only need this point on curve here. So I'm going to do one thing. I'm going to shatter this line here, reparameterize it using one single parameter. And this parameter is going to be a natural slider, which is the default slider that you get when you go into params, input, number slider. This is a natural slider. Natural meaning from 0 to 1, okay? Because every time you reparameterize something, this is the normalized, sorry, not natural, normalized slider, okay? So when you reparameterize thing, everything becomes between 0 and 1, okay? So reparameterize is also called normalizing, okay? So this is a normalized number slider between 0 and 1. And if I do this, I am basically splitting the vertical body into 2 segments, okay? One, actually this is a linear curve, so this is actually splitting the line like at 1/4 of its length, okay? And this becomes visible because I also need a point here. So I am going to evaluate the curve, reparameterize this curve, and applying the same parameter here. So this is the point of the evaluate curve, and it's also the splitting point that it's creating these 2 segments from the shader component, okay? So if I do this, I am both creating a point and using that point or splitting the line at this height, okay? So here we have a different set for our system because the point on curve is no longer our anchor point or our end point for the springs. It is this one. And also, so these springs here must converge into this point. So I'm going to substitute the point on curve with this point here. So you see, these are the new springs. And also, I must keep things collinear, not with respect to this point on curve, but to this evaluate point here. And so I am substituting this point on curve inside this point for the collinear goal. Now I can do this with one single operation because I need to substitute this point on curve with this evaluate curve point. So I shift sorry, control shift and drag these cables from point on curve to this the output of our evaluate curve point. So I can get rid of our point on curve. Now we have two things here to consider. This point is already being kept collinear by this collinear command here. Now the problem is that we have two segments here that we want to consider instead of the whole line as bar. Okay, so I must disconnect the whole line from these bars here and plug the new segments to this. Now the problem is that in this case, for example, the collinear is not basically bounding the vertical line to this center point. Okay, the collinear is basically keeping all the endpoints of these two bars collinear. Okay, so what I'm going to do, I'm going to hide and reset all the simulation. Okay, and run the simulation again. Now, this system, you see that when the body falls down, these springs here follow the position of this inner point. So, for example, if I increase the module, the intensity of the load, you see that this thing is kept perfectly in place. Okay, so this is the correct behavior for this system. Okay, not the previous one. Of course, things can go bad very quickly when you start to increase these values here at very extreme intensity, for example. Okay, but anyway, you see that the range that I gave to these sliders here is pretty good. Okay, so this is due to some kind of amplification of the bouncing. Okay, so it's some kind of resonance happening here. So due to resonance, extremely rigid structure or control structure can also fall down. There is a famous example of a bridge that fell down due to resonance oscillations provoked by wind. But anyway, in this case, you see that if I move slowly, the system always maintain its equilibrium. Okay, but if I do something, some change, if I edit these forces very quickly, then there can be some bouncing that destabilize the system and make it possible for it to, yeah, okay, that's it, to enter some kind of resonance effect, and you see that everything collapses. Okay. But anyway, this is something that eventually you might want to consider when tweaking the values. Do this with extremely, let's say, soft movement or soft edits. Okay, don't do extreme changes in your system. Of course, this system becomes more and more stable as I displace this point along the shaft of this bar upwards. Okay, because this bar is anchored only in this lower part, but if I raise this point up, I will create a more wide triangle, which is more stable and encompass all the length of this bar. So it becomes more stable. Okay, but this is just basically tweaking this slider here from the evaluate curve and shader. I just move it up. Remember that Kangaroo doesn't like real-time changes in the geometric system, so you must reset the simulation, and here it is, the new configuration. You can run it and it becomes more stable, especially in this inner part. So basically what we are saying is that the upper line is totally irrelevant in our system. So the upper line is a separate bar which is kept in place by a non-existent physical body here that is just making this point collinear with this one and this one. So this is just fake in our system, okay, in this moment. But we need it in order to have the bar, let's say, anchored or connected to its center body, as these two things will be able to slide mutually in an uncontrolled way. Okay, so this is the proper representation of our system. So even if the geometric system doesn't have any control over this vertex, we need it, because if we do not apply this little segment will be able to fall down aside of this point here. So if I don't use collinear here, this bar is no longer forced to be collinear to the segment below. So for example, if I reset these and start tweaking things, you see that the upper segment just fell down and it's no longer visible. Okay, so that's why we must use this kind of controllers along the system. Okay, and this is important because normally you not always want to anchor or to fix the cables to the endpoints of the bars. Okay, you can also you might want to fix cables to inner point or to midpoints of your bars. In that case, you must apply this kind of controls. Okay, you can also solve the problem by let's say providing different controls which would avoid, for example, this scenario here. For example, there are other goals inside the goals line, for example, where you might want to work, for example, with I don't know, if in case you define a midpoint here, you could work with equal length, or you can always find another way. But I find that constraining with some goals is the more effective way of creating this kind of tensegrity systems. Okay. So yeah, basically that's pretty it for this thing. And if you want to, let's say, keep this the proper aspect, you might want to separate the output. And in that case, for example, just in order to fix this concept here, I will plug all the lines. Well, actually, these are the bars. Okay, I will plug the bars to branch 0, 0. These are the cables 0, 1, and all the rest of the goals are going to be in anchor, load, and collinear into branch 0, 2, and plug this here. So nothing changes in the system, in the simulation. And I will take this output here and partition list it and three statistics of this and partition it with this length. So here are our output, and I explode the tree, and 0, 0, 0 is all that I need. Okay, these are my bars, and what I want to do, I want to give thickness to them. Well, one easy way is to use a pipe. I don't recommend to use a pipe normally. So in this case, for example, let's give this a smaller radius and caps flat or round if you want a more aesthetic representation.
Why you don't recommend to use it?
Because pipe is it's very heavy. It's a very heavy component. So, for example, if you, I do recommend when you work with Grasshopper that you visualize some widgets, especially the profiler. So the profiler gives you an idea of what are the most, let's say, time-consuming and processor-consuming components in your definition. And normally, especially when you work with several geometries, the pipe is one of them. Okay, so it makes your simulation run in non-real time because it's very, very heavy. Okay,
Is it another component that makes the same trick and is faster, or
mesh pipes normally, because with mesh pipe you can change the resolution of the mesh according to some sliders, while here the resolution of this pipe is determined only by this low quality, high quality. But this is like in Rhino. Okay, so for example, when you create a sphere in Rhino and switch to shaded viewport, then this is the mesh which is basically associated to the original wireframe object. But this mesh here depends on Rhino settings for creating meshes dynamically or automatically. And these settings here are in Rhino settings. Let's wait for it to open. in Rhino settings, I'm just, I want to show you that here you have render mesh qualities by default set to jack them faster. So this is a very low quality for Rhino, but you see that it looks like a perfect sphere. Okay, so when Rhino and therefore Grasshopper say low quality, you are already getting a very high resolution for these pipes. Okay, so you see that all reflections are quite smooth. So I wouldn't recommend you use this comment here normally. So just refer. Oh, also you see this. We have two poles here, two bars. Then you have this overlapping here. But anyway, this is just let's say a detail. But anyway, I am just working with 5 bars, so it's not a problem in this moment. But you see that when you run this simulation, pipe says 7 milliseconds, okay? And it starts 8 milliseconds also. Now, this might look 9 milliseconds also. Now, it might look like a very inexistent time, okay? But you have to consider that this 7 milliseconds means that each time the processor calculates something, 7 milliseconds are occupied by this pipe. And a processor, the CPU is very fast. So when it calculates 7 milliseconds, it's a lot of time. Okay, so that's why I do not recommend to use the pipe. I do recommend you use mesh pipe eventually.
All right.
Anyway, there are also other components, other plugins. For example, actually, I'm working with this, which is called Dendro. Dendro is a plugin that gives thickness to let's say non-3-dimensional geometry. For example, curves, points, also surfaces, for example. So it gives thickness to objects. And it's very interesting. It basically substitutes or arrived to substitute this other plugin, which is called Cocoon, which was doing the same thing, but it is lower. Okay, so I'm actually switching to Dendro. But anyway, we are not going to discuss this. I invite you to take a look at these plugins because they are very interesting when you want to create some very particular shapes, especially when you work with organic shapes, not like this. So in this case, you see we have separated the bars from the tendons with these exploratory methods, and we can work with them in several ways. Okay. So this is the actual aspect of this system. I'm going to share the picture in this definition before sharing it into the YouTube video. Okay. So yeah, that's pretty it. I'm going to turn this off, reset it, and group it, and deactivate this group, and also change the color to red, and also create a jump between this and also this, and make this belong to this group. Okay, and now these two things here, well, basically are simply more complex systems. Okay, now this is one interesting system. It begins to be quite complex, and I wanted to point out this system not because it uses some different goals. You see that it is always based on springs and anchor points in this case. So there is no collinear, no need for collinear, but I wanted to point out the complexity of creating this kind of geometry. And this is a mid-level complexity, okay? The next one is going to be way more complex, as you can see. But in the end, you always have springs. Oh, and I wanted to point out the use of the old version of Kangaroo. So it's always springs, load, and eventually, well, it's not anchored because it doesn't need to be anchored, the next one, but anyway, you will see it in a while. Now here, for example, I needed to build this huge complex tensegrity system, and I'm going to hide the output, and I'm going to focus on the first part. I'm not going to recreate this from scratch because, as you can understand, this is not healthy. Okay. So what I'm going to point out here is the basic here, which is this arc. which is divided, in this case, using perpendicular frames, so I can decide how many, let's say, splittings occur along this arc, and this will also change the complexity of the resulting tensegrity system. And with correspondence to each perpendicular frame, I create a polygon. Now I'm working with triangles, of course. In this case, this is an upgrade, let's say, to this structure here. Okay. Now the problem is, okay, everything is quite smooth up to this moment. Okay, but things become very complicated when we must start from this and start creating bars and bars and springs. Okay, so of course I have to explode all of these triangles here, but now I have quite a complex data tree. So each triangle is originating a data tree, sorry, a branch here. And so we had 10 division here, which originates 11 frames. So we have 11 branches here, each one containing 3 points. Okay. Now, what I'm doing here, I'm creating these things here. Okay. So I need to create, these lines are going to be the bars. Remember that, take these as a triangular prism, like the one we have used for the first definition. Remember that diagonals were the bars, and then we need the cables, which are basically the polygons themselves, and also the vertical connection between two different frames along the arc. Okay, so this is the first lines, and this is pretty simple. In order to achieve this, I need to take the first branch of points and the next branch of points, shift the next branch one position in order to connect this point with the next point of the second set, this point with the next point of the second set, and this point with the next point of the second set. But this happens also for, let's say, frame number 0, frame number 1, but then there is also frame number 1, frame number 2, and it's the same thing. So what I'm doing here, I am shifting this list here of points by using a shift of 1. Okay? So what happens here is that we flip the matrix because let's take a point list in order to make it visible. You will see that things start to be crazy with this definition, but there is no other way to create this system by default. Maybe someone should create a plugin or some quick cluster of components in order to create this basic tensegrity structure, like with a few clicks. So if I take this, you see that we have points grouped by polygon, 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay. If I flip this matrix, I get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 11 points along the arc. Okay. If I shift list, what I'm doing, instead of having, let's say, instead of having 0 at the inner part of the arc, I shift list and I have 0 on the next corner. Okay, so I am creating this shifting for each section, basically. And once I do this, I flip the matrix and I have the same range, 0, 1, 2, 3, 4 along the arc. But the thing is that this flip matrix is actually with its first branch, it's the inner part, the black branch, you see? While the black branch of this other shifted list is on the first corner of the triangle, okay? So when I do this, I do also this thing, explode this tree, so I have access only to the first line here, and explode this tree so I have access to the first line, which is this one. Now, if I connect this branch with this branch directly, I will get this straight line connecting this side of the original triangle. Okay, so if I take a line from point A to point B, and plug these and these, I get these connections. But I don't need these connections here because I'm creating the bars right now. So in order to create the bars, I must take this second set of points and shift it one position forward. So this point will connect to this one, and this will connect to this one, because this is going to be the new 0. Okay, so that's why you see there is another shift list that simply does this. Okay, you see that now this has become 0, 1, 2, 3, 4, 5, 7, 8, 9, and that's it. Because if I tell the shift list that I want to wrap the values, I will get the point number 10 here, and I will get also a connection between this point number 10 and eventually this point number 10. But I don't need it because I don't need this diagonal here, this bar. So I ask the shift list to not wrap the values. So it's like wrapping is pushing the values one position forward, and this value here should be pushed away from the set unless I tell wrap the values, and instead of being pushed out, it would be pushed in the first position. But I don't want this, okay? So in this case, I'm shifting this, and I'm creating the line correctly, okay? And I have to do this for each bar that I want to create. So you see that there is always the same thing. The first set of points remains untouched after the flip matrix. I just explode the tree. And the second set of points, which is basically the next frame, it's exploded, and it is also shifted one position forward with wrap set to false. And this allows to create the 3 sets of bars, which are these 3 set of lines here. Now here, I am calling this because you see that here, if you do this, basically you get 11 lines, while we only need 10. Okay, so if we take a look at this preview, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, we only see 10 bars. Okay, but if we take a look at this, there is also this one, because even if we didn't wrap the output, there is always one last point here that is taken into account. It's creating this bar here. We don't need this, but this is simpler than doing some data manipulation here for creating the lines. I prefer to create all the lines here, and you see it creates also this one and this one, and get rid of the last one, because the last one depends always from how many separation or how many division we do along the arc. So basically, if we get one line more than necessary, that line will be inside this list, and its index is going to correspond to the amount of divisions that we operated along the arc. And the amount of division is basically defined by this slider here, which defined how many frames we had. And so if I create a call index, I'm saying, see this list? I want to eliminate call the element which has the index equal to the number of divisions. And therefore, we get here our 10 lines. And these are the 10 lines that we are going to use as bars. Okay, here they are. We got rid of this triangle here at the end. So you see that defining the geometry is always the more complex part. And actually, it's more or less the same thing that I did here to create the cables. Okay, so once again, there is, in this case, there is a particular situation here that happens in this system. If you want to create the Tensegrity system using this structure here, you must also, let's say, define a different approach to the structure. You see, let's give a quick look. I took the polygons, you see the original polygon, and rotated it in by basically, this is the same characteristic angle for the triangle. You have to consider, for example, that in order to create a let's say, a rotation that brings the vertex with corresponds to the midpoint of each side, you have to consider that the characteristic angle of the triangle is 180 divided by the number of sides, so it's 60. Okay, so you see that here you have basically the same thing, but we are defining this like 360 divided by the number of sides, and then the number of sides multiplied by 2. This is not exactly correct. It should be 180 divided by this value. But anyway, it was just to avoid creating another layer of complexity to this thing and work with very understandable parameters. But anyway, we have the rotated triangles here. This is discontinuity that is giving us access to these points, and these points here are being used to create this additional set of lines. Now, let's take a look at.
And basically, they are rotated 60 degree.
Yeah.
So they're in the middle of the other points.
Well, actually, not exactly in the middle, because you see, we should have you should think that there is a side here for the triangle. You see that this point is at half the length of the triangle, but it's out of the original triangle. Okay, so it's at the same level, but out of the original polygon. Okay, now let's it's already we only have 8 minutes, but let's say that this definition, I'm going to share it with you, so you will be able to play with it and see what's the meaning of all these things. What I wanted to point out is where we are going with this simulation. Let me there is some points that's turned on. Yeah, okay, it's the flip metrics. Okay, so let's see where we are going with this. Okay, so these are basically our set of bars, and here at the bottom we have the springs. So here we have, this is the final structure that you need in order to create this system. Okay. There is also a different approach to this particular tensegrity structure. I'm going to simply make a quick sketch here. There is another way of creating this, but it works with two crossed bars. Like, for example, you have two crossed bars like this, and you create another set of crossed bars, but in a perpendicular frame. So if this is the frame containing these two bars, you create a perpendicular frame like this that overlaps with the first one, and then you create your bars in this other direction, and then you create wires and elastic connection between these points, and also elastic connection like here and here, and then anchor this frame by frame with the next frame and the previous frame. But this is another type of tensegrity structure. We are not going to discuss this. But in this case, in order to maintain all these poles or these bars anchored, you need to provide, remember, always 3 cables per each bar endpoint. Okay, so this makes it more complex to create this structure. That's why I rotated the triangle 60 degree. You can also start directly with an hexagon if you want. Eventually it becomes more simple, but you will have to play around with these shift lists and so on in order to create the proper connection scheme. Okay, I prefer to use the rotation, but it's absolutely the same. So you have the bars, which are always 3 per section, and you have all these springs necessary to maintain this object in position during the simulation. Okay, and so you see that once you define the structure, everything goes back to the usual behavior. So you must provide bars quite a huge amount of strength in order to don't deform, and then you provide pre-stress to the cables. And then there are some anchor points here, which are basically the anchor points at the two connection point of the arc structure to the ground. Okay, and that's it. So once you have the simulation, this is quite a heavy simulation, as you can see, but also because there is this thing that I did with Dendro, exactly. I do recommend that you, well, actually, what I'm going to do, I'm going to get rid of this, disable it. So it's going to be faster, as you can see. And I'm just going to concentrate on the clean tree. You can implement the exploded tree strategy to this, and so you must sort the goals into an entwined tree, so you can create the exploded tree method. And this is what happens. Okay, so you see this structure tends to fall down because of the load that we are applying. Well, actually, this is only working with pre-stress, so there is no load actually, but you can apply it with a load component. So anyway, you see that these pre-stressed springs or cables tend to contract, and this basically shrinks the structure, which tends to fall down a little. Okay, and this is quite nice. You can also play with pre-stress if you want. This is relaxing, and this is contracting. And it's nice to see how the deformation occurred without changing the length of the bars. So for example, eventually the planar frame starts to, let's say, lose planarity because the bars are kept with a constant length, and the springs are contracting way too much in this case. But anyway, you see that this thing is capable of finding its own new equilibrium state. And this is important because if you pre-stress this very much like I'm doing right now, this structure here tends to be more resistant. So you can apply a higher load to this structure and it will deform less. It will fall down less. Okay, so that's the general principle of tensegrity structure. Okay, so you can play around with this definition. I will leave it like this, like very, very heavy pretensioning. Okay, so you will be able to use loads in your definition. And also in this case, for example, just so that you have a look at what Dendro does to this. These are the poles, the white one, and these are the cables, the black one. Okay, so it's like taking the curves and give them some volumetric representation. It's based on boxes. Okay, so if you are used to work with meshes and boxes, you know exactly what it means. I am not using the smoothing. There is also smoothing in Dendro, which is quite interesting. This is still some, let's say, discrete mesh representation with polygons very visible. But you can smoothen this geometry in order to get a more nice aspect for them. But anyway, eventually what I'm going to do right now, I'm going to get rid of Dendro because I don't want you to be distracted by it. So let's go back to our explode tree. And what I did here was basically apply a partition list soon after the clean tree, because remember that Grasshopper doesn't change the way that data is sorted inside the data sets unless you want to. So I just took these two sets of lines, calculated the amount of lines contained into each one, and used these values to create a partition list. This is something that you can do at once playing with the entwine and the tree statistics during the before and after the simulation. But this is exactly the same results. So if I take a line container, you see that these are the bars, and on the other end you will have the springs, the cables. Okay, so I will leave it like this. So you will have access to this result here. And is it set to false? Yes. Chat. Let's see what happens with the chat. That's blow your mind definition. No, Ariel, this is not a blow your mind definition. What comes next is going to be the blow your mind definition, because the next one which is, it's curious because this was the first Tensegrity system that I created. That's why it's made with Kangaroo 1. Let me see. Wow, okay. So this is basically a definition that I made when I was studying Tensegrity system applied to Platonic volumes. Okay, so the icosahedron, for example, which is way simpler than this. It's a nice structure because in the end, it creates a configuration of pentagons and triangles, which is something that you can see here. The fact is that I want to create a sphere, basically, an elastic sphere made up with a tensegrity structure. Okay, so the problem here is that you cannot simply take a sphere and create a set of points over the sphere and then just apply bars and springs, because there is basically no standard way of creating a spherical geometry and producing a grid of points like pentagons and triangles like this one. Okay, so this is what you need to have if you want to create this kind of polyhedra representation. Now I increased the amount of vertices, basically, so I increased the amount of bars and springs, but this is what you have here. And you see that the bluish one are the bars and the yellow one are the springs. So what happens when you run the simulation? This is the old Kangaroo, by the way. So in order to work with this, you need to install Kangaroo 099. So just so that you have it clear, is this one, where you have just forces, Kangaroo, mesh, and utility. It's not like Kangaroo 2 with goals divided by type of goals or type of actions or type of geometry. Okay, so you need to work with this. And I find it, yeah, you see that it's written here. The creation of the geometric system is basically independent from the version of Kangaroo, but here this part is all based on Kangaroo 099. Okay, and therefore you see here at the end you have this custom preview here, and I'm going to run the simulation. This works a little different from Kangaroo 2. You have this double click on this on the solver icon, and this control appear when you can run the simulation like this. And you see that springs start to work, and you have this final configuration for the system, which is all made up of pentagons and triangles like this: pentagon, triangle, pentagon, triangles, pentagon at the bottom, and so on. Okay. Now the trick is that if you want to increase the amount of polygons a little more, you will have to work on this area here, and you don't want to do it. Okay, I'm not even going to analyze this. You can do it by yourself. It's pure geometry and connection and endpoints and lines and so on. So it's very basic grasshopper use. I am quite sure that today, if I should do this from scratch, I would not use the same method. But anyway, I was quite rookie at that moment, so this is the only thing that came up to my mind. Okay, but anyway, for example, here there should also be some load. Yeah, there is some load. In this case, in Kangaroo 099, things works a little different. So gravity is set to 0, so this object is not falling. As you can see, it lies at more or less 1 unit up from the ground floor. And the ground floor, there is no floor goal in Kangaroo 099. You just have to use Kangaroo settings and say that floor is set to true. Okay, so there is already a floor acting in this simulation. And if I use gravity, give gravity a negative value or a positive value, these things start to fall up. And if I use a negative value, these things start to fall down and then bounces on the floor. Okay, like this. Now remember then that floor, even in Kangaroo 2, floor is not a constraint, is a collision object. So you see that in this case, the collision object is applying a force to the system, which is more or less equal to the global strength that is producing this object falling down. So Kangaroo tends to vibrate like this. When you see this, don't um, don't keep on increasing the values. Eventually decrease the values, because it means that Kangaroo is becoming unstable, and this can crash the simulation. And if Kangaroo crashes, you have to stop and reset everything, if you're lucky. If you're not lucky, Kangaroo crashes and Grasshopper crashes as well. Okay, so just when you see that things start to vibrate like this, then just set everything back to 0, or avoid the critical configuration of parameters. Okay, and yeah, this is a complex system actually. So you can play with it. You can take a look at how it is done. You will see that it is very basic Grasshopper use. There is no rocket science here. It's just lots of connection, because the way that, especially because of the elastic cables, okay, the way that you must connect these cables is one specific way. And if you study, for example, the icosahedron definition as a tensegrity system, you will also find out how these cables are connected. These lines are connecting these wires here. So it's just analyze the base model in order to develop this more complex one. But it's extremely simple. What you could do eventually would be to substitute Kangaroo 099 with Kangaroo 2. You can also get rid of all this stuff here and just take the output of this part and plug it into a Kangaroo 2 simulation, which is very simple, because we are only using springs and loads. There is no other thing here. And you will only miss a floor, because in Kangaroo 2 you need this additional goal if you want to apply a floor to your simulation. Okay, but this is it's very stupid. It's impressive, but it's very stupid. So that's it for the tensegrity part. Do you have any question? Do you want to? Last definition is very interesting, because it's all about the same principles, no matter what is this. Yeah, actually, yes. But as I told you from the first definition, the complex thing here is the correct definition of the geometric system. So once you have the geometric system set up properly, and you have differentiated between bars and cables, then you can simply apply Kangaroo. And Kangaroo is very simple, because you are only dealing with springs, be the springs more or less elastic, so bars or actual springs, and eventually loads, and eventually anchor points, and that's it. So it's very simple. And if you have complex system where springs are not connecting endpoints but midpoints, then you also must work with some co-goals, like the collinear that we saw here. But tensegrity, it's simple. The problem is defining the system in the proper way. Okay, so I will share with you also a screenshot from the complex tensegrity system that I've been creating with this company I'm working with. And yeah, and you will be able to have an idea of what it means to work with a complex tensegrity simulation. Tell me, Tiziano.
I have a couple of questions. The first, really basic, the spring in Kangaroo 2 is length line.
Yeah.
The component, right?
Yeah.
Okay, that was really easy. The other is like, if you have to simply sketch with a pencil the principle behind the Palazzo dello Sport, will be possible this time, next time, to have just an idea what is the principle behind the tensegrity you made in the definition with a sketch, not without all the components and so on, because now that we are fresh with.
Well, actually, what I can tell you is that if you know the Sport Palace, you know that the dome is made up of two different levels of structure. There is a principal structure, which are these huge beams like truss, which have this arc shape that go from one side to the other. And then there is the secondary structure, which is basically necessary to just maintain the copper panels that basically provide the covering of this dome. Okay. Now, what I can tell you is that if you want to work with, if you want to convert this structure into a tensegrity structure, you cannot work with two separate structures. Okay, you have to change the way that the two structures work together. They must work together in order to create the tensegrity system. Else, it won't work. So there is some structural adjustment in this in the actual configuration, but not in terms of the geometric system. You must understand that there cannot be one principal structure and secondary structure. The two structures must work together in order to create one single huge tensegrity system. Else, it will collapse, basically.
Okay.
Okay.
And the last, just curiosity,
Yeah.
if instead of 60 degrees in the triangle we place, for example, 80 or whatever, will the system collapse in the previous
this will
definition?
affect, I think this will affect the torsion, okay? But we can do this. We can just take a look at this because this creates some asymmetric stress inside this each of these frames, okay? So I don't think it will collapse because in the end, for example, if you think in per sections or per chunks, for example, this chunk is maintaining equilibrium because of this action and this action, okay? So I don't know, actually, let's give it a try. We have this, oh yeah, we are working with radians here. So let's do something very stupid. I'm going to add, here, I'm going to add a slider between 0 and the 90 degree, no, it's too much, 6. Yeah, okay. So I will do this and use the result as the rotation angle, okay? Now, for example, if I add half, this value should be P is 180 divided by 6, it means 30 degree. So this is something like 15 degrees additional rotation, okay? So if I reset this simulation, why I'm not seeing this reflected here? Let me check what happens. Oh, sorry, this is 0.2 degrees. Sorry, this is 0.2 radians. So it's already, no, I'm just, rookie mistake once again. So basically this is already 60 degree. I have to add degrees here, not radians, sorry. So basically I'm going to change this slider between 0 and 15. Okay. So in this case, yes, I have some kind of visible effect. I'm taking 15 and I'm hiding this and reset the simulation and run the simulation. Yeah, you see that there is some more, let's say, visible effect. There was more twisting. I don't know if you were able to see, but you see that, for example, this part here is way more compressed than this part here. And this is due to this angle. And as this is a geometric change of the system, this is something that you cannot do in real time, you see. So this is not affecting the whole system. This is only affecting the first portion of it. So you cannot do this in real time and see what's the behavior of your system. You should eventually, if you want to do this dynamically, we have not discussed this because it is not part of this. Basically, all that we are doing is based on rigid bodies, more or less, okay? While if you work with Kangaroo for simulating soft bodies and textiles and so on, then it makes sense to consider, let's say, variable condition for your geometric system. In that case, you might also apply a geometric variation to the system, but not like this. You must consider, for example, different properties or different behaviors, like the one that it's easily, let's say, visible here in the anchor point. The anchor point is normally fixed, but you can tell the anchor point that during the simulation, it will have to move towards the target anchor point. And in this case, for example, if you, let's say, create a parametric displacement of the anchor point and plug it into target, then you change, for example, the amount of displacement, and Kangaroo will take it into account dynamically because the anchor point is actually moving during the simulation. Okay, so in that case, you can work with a variable geometric system. And this can also be valid for things like this construction that we made here. But it's a little more complex to create it. So yes, you can do it, but not in this moment. Okay.
Sorry.
Yeah, sorry. I wanted just to point out that what you can do, for example, is take this simulation here with a 60-degree rotation, wait for it to converge, which is happening anytime soon. Well, this is micro adjustment occurring here. You see that the iteration keeps on going, 4,000, 4,500, and so on. But basically, the system is already stabilized, so you can turn it off and eventually bake all of this thing and have it here in Rhino. Then reset the simulation, go back here and see what happens if we increase the rotation angle, and then we reset the simulation, run the simulation again, and you will see that there is a different configuration for the system. This depends on the twisting that we are providing with that angle. So let's turn this off, and also let's bake this in order to have the two versions. So I hide Grasshopper, and we have this version and this version. Okay. But this would be nice.
So
yeah.
There is no rule. There is no rule of thumbs that say that more than 60 degrees your simulation will fall down. You choose 60 degree because it's the approximation that make the triangle more or less in the middle axis rotating.
Yeah, remember that it's like having this. Okay, so let's say, for example, you have this this huge structural element with a constraint here at the floor like this. Okay, and you don't want this to fall, so you have this is free to rotate in 3 directions. Okay, why? Right? So if you have this, okay, and you don't want this to fall, you have to anchor this to the ground using at least 3 cables, right, in a triangular distribution. Okay, if you don't do this, this pole will be free to move around. Okay, so the concept is that you can change the position of these 3 points and still maintain this pole in position. So I can take these 3 points, for example, and rotate them into different positions like this. Or I can also take these 3 points and shrink this triangle a little. For example, if I take this and move it like here, I will have a different shape for this triangle, but still I will have 3 connections. So this pole will be kept in place as well. So it's not that if you change the angle, the system collapses. It finds a different configuration. As soon as you have 3 wires connected to this point, this pole here will stay up. Okay, so that's the same thing applied to our system. I just choose 60 degree because it was symmetric. That's it. There is no actual specific need, and also because this kind of structure eventually it's convenient to work with a symmetric structure because it's easier to fabricate it. Okay, so you have all the springs have a precise length, while if you choose a different angle, you will have some cables with different lengths. It adds complexity, for example, to constructing the system in real life if you want to build this tensegrity structure in real life. Okay, so that's the only reason why you should use a controlled rotational angle.